Welcome to Chapter 12 on Clustering and Unsupervised Learning. Here we explore how to find structure in data that carries no labels at all. Every chapter so far handed the algorithm an answer key. Now we enter unsupervised learning, where the data has features but no labels, and the goal shifts from prediction to discovery. By the end of this chapter, you should be able to contrast supervised and unsupervised learning, say what makes a clustering good, explain how k-means works, and use the elbow method and silhouette score to choose the number of clusters. You should also be able to read a dendrogram from hierarchical clustering, describe how linkage methods change results, explain how DBSCAN finds clusters by density, and say why feature scaling is critical for distance-based methods. This figure shows k-means with 3 clusters. Each point is assigned to its nearest centroid, marked with a cross, and the centroids are updated step by step. The colors show which cluster each point belongs to once the algorithm settles. Unsupervised learning is simply machine learning without labels. Its tasks share a flavor of exploration, grouping customers by behavior, organizing documents by topic, spotting unusual transactions, or reducing many features to a few informative ones. Another example is finding hidden structure in survey responses. Because there is no answer key, unsupervised learning rarely produces one provably correct output. Clustering is the task of partitioning observations into groups by some chosen measure of distance. We want high similarity within clusters, so members of a group sit close together, and low similarity between clusters, so different groups stay well separated. Clustering and classification both sort observations into groups, so beginners often confuse them. In classification, the groups are known in advance, and you have labeled examples of each one. This figure contrasts classification with clustering, making the difference between known labeled groups and groups we have to discover easy to see at a glance. Almost every clustering method rests on a notion of distance. Let us look at a few common ways to measure it. 3 distances come up often. Euclidean distance is the familiar straight line measure, best for numerical data. Manhattan distance sums absolute differences like traveling a city grid. And cosine distance compares the direction of 2 vectors rather than their magnitude, which is popular for text. For 2 observations described by 2 features, Euclidean distance is the square root of the square difference in x plus the square difference in y. The same idea extends to any number of features by summing the square differences across all of them. Here is a pitfall that trips up newcomers constantly. The 2 standard fixes are standardization, which rescales each feature to mean 0 and standard deviation 1, and normalization, which squeezes each feature into a fixed range. Always scale before any distance-based method. The key point, scaling is not cosmetic, it changes the answer. Because clusters are defined by distance, an unscaled feature with large numbers will hijack the result. Standardize or normalize your features before clustering every single time. K-means is the most widely used clustering algorithm, and for good reason. It is simple, fast, and surprisingly effective. K-means runs an elegant back and forth. Choose the number of clusters, place that many centroids at random, assign each point to its nearest centroid, then move each centroid to the mean of its assigned points. Repeat until the assignments stop changing. This figure illustrates that iteration. Assign points to the nearest centroid, recompute each centroid as the mean of its cluster, and repeat until the centroids stop moving. The assign and update loop is much easier to believe once you turn the crank yourself. Picture a marketing team with 6 customers, each summarized by 2 standardized scores, a spending score and a browsing score. Here are those 6 customers, described by 2 standardized features. We will cluster them into 2 groups entirely by hand. K-means is trying to minimize the within-cluster sum of squares, the total square distance from each point to the center of its own cluster. Equation 12.1 writes this out, summing the square distance from each point to its cluster centroid across all clusters. In that equation, the term mu sub k stands for the centroid, the center of cluster K. K-means must start somewhere. A common choice is to seed the centroids at 2 of the actual data points. For the first iteration, we assign every point to the nearer centroid, measured by square distance. Here are the iteration 1 assignments. With both seeds sitting on the left, cluster 1 captures only A and B, while cluster 2 sweeps up C, D, E, and F. Now we update each centroid to the mean of its members. The first lands at 1.5, 1.5, and the second moves out to 6.75, 2.25. On the second iteration, point C switches back to cluster 1. That gives a clean split, A, B, and C in one group, D, E, and F in the other. We update again. The first centroid becomes 2, 2, the mean of A, B, and C, and the second becomes 8, 2, the mean of D, E, and F. Reassigning with these centroids leaves every point exactly where it was. A, B, and C are closest to the first, and D, E, and F to the second. The algorithm has converged. This figure traces the whole hand calculation. Both centroids started on the left, and the arrows show how they moved over 3 iterations, with the second centroid sweeping right to 8, 2, as it gathered its points. This tiny run also exposes 2 facts the chapter keeps stressing about how K-means behaves. Picking the number of clusters is the central decision in K-means, and getting it wrong distorts everything. The elbow is not always sharp, and sometimes the curve is maddeningly smooth. For all its popularity, K-means has real weaknesses. You must choose the number of clusters in advance. It is sensitive to scaling. Its result depends on where the centroids start, and it assumes clusters are roughly round and similar in size. It also performs poorly on elongated or irregular clusters, and outliers can drag a centroid off course. The dependence on initialization has a standard remedy. scikit-learn runs the algorithm several times from different starts and keeps the best. Hierarchical clustering takes a different stance. The agglomerative bottom-up version starts with every point as its own cluster and repeatedly merges the 2 closest. The divisive top-down version starts with one big cluster and splits. Agglomerative is far more common. That hierarchy is displayed as a dendrogram, a tree diagram recording the order and closeness of every merge. To get a specific number of clusters, you draw a horizontal line at a chosen height and count the branches it crosses. This figure shows an agglomerative dendrogram. The leaves points A through E merge from the bottom up, and the height of each join records how different the merged clusters were. Cutting at the dashed line yields 2 clusters. When merging the 2 closest clusters, we need a rule for what distance between clusters even means. Single linkage uses the nearest pair of points and can chain clusters into straggly shapes. Complete linkage uses the farthest pair and tends to produce tight, compact clusters. Average linkage uses the average distance over all cross-cluster pairs, a middle ground. Ward linkage merges the pair that raises within cluster variance the least, and it is often the best default. Since linkage changes the result, it is worth trying a couple and comparing. DBSCAN, short for Density-Based Spatial Clustering of Applications with Noise, approaches things from a different angle. Two parameters control it: how close points must be to count as neighbors, and how many neighbors anchor a dense region. It shines on irregular shapes and outlier detection. This figure shows how DBSCAN labels points by density. A core point has many neighbors within its radius. A border point lies within reach of a core but is not itself dense. And an isolated point in sparse space is treated as noise. This table compares k-means, hierarchical clustering, and DBSCAN side by side, summarizing how the common clustering methods differ. A practical habit is to start with k-means for a quick read, reach for a dendrogram when you suspect nested structure, and turn to DBSCAN when clusters look irregular or when outliers are the whole point. Evaluating a clustering is genuinely harder than evaluating a classifier because there is usually no ground truth to check against. 4 approaches help: visual inspection, plotting the clusters to see if they look coherent; domain interpretation, asking whether the clusters mean something to an expert; the silhouette score, a numerical measure of quality; and external comparison, if any labels happen to exist. The silhouette score deserves a closer look. Still, it is wise to treat every metric with healthy suspicion. For practice, we will use the wine dataset from scikit-learn. It records 13 chemical measurements for 178 Italian wines grown by 3 different cultivators. This code loads the wine data, standardizes the features, and runs k-means asking for 3 clusters. It then reports the silhouette score for cluster quality and the adjusted RAND index, which checks how well the clusters match the known cultivators. In short, we standardize the 13 features, run k-means with 3 clusters, and report those 2 scores. In a genuine unsupervised problem, of course, you would not know in advance that 3 clusters is the right answer. This code applies the elbow method. It fits k-means for a range of cluster counts, records the inertia each time, and plots inertia against the number of clusters so we can spot where the curve bends. The inertia attribute reported here is exactly the within cluster sum of squares we discussed earlier. The same scale data can be clustered hierarchically with a one-line change of method. This code fits agglomerative hierarchical clustering with 3 clusters using ward linkage, then counts how many wines land in each cluster. Here we use ward linkage, the usual default when we expect compact clusters. Finally, we try DBSCAN, which decides the number of clusters for itself and may flag some wines as noise. This code runs DBSCAN with a chosen neighborhood radius and minimum sample count, then counts the points in each resulting cluster. Note that a cluster label of -1 marks a point that DBSCAN considers noise rather than part of any cluster. In our case study, a subscription streaming service wants to understand its subscribers without imposing categories from above. It has behavioral data on each account but no labels, so it turns to clustering to let the segments emerge on their own. This is a textbook unsupervised problem because the company has no predefined customer types. Discovering them is the whole point. The first steps are to assemble the behavioral features, clean the data, and scale every feature so hours watched does not swamp the rest. Next, run k-means across a range of cluster counts, using the elbow method and silhouette score to settle on a sensible number. Cross-check with hierarchical clustering to confirm the same groups reappear, then profile each cluster by reading its centroid in plain words. Then hand those profiles to the product and marketing teams to act on. The service might find heavy daily viewers loyal to a few genres, light weekend-only watchers, and a small cluster that subscribes, binges, and leaves. 2 cautions carry over from the chapter. The code below demonstrates this customer segmentation workflow using the wine dataset as a stand-in for the behavioral data. This code scans several values for the number of clusters, reporting a silhouette score for each, then fits the best choice and prints the average of the first few features per cluster to profile the segments. Scanning silhouette scores points to 3 clusters as the strongest choice on the wine data, and the cluster mean table reveals the distinct chemical profiles that separate the 3 discovered groups. To summarize, unsupervised learning works on data without labels, and its flagship task is clustering, grouping observations so each group is internally similar and clearly distinct from the others. For further reading, look to the foundational paper that introduced the k-means algorithm and the paper that proposed DBSCAN and density-based clustering. That brings us to the end of Chapter 12 on clustering and unsupervised learning.